Hey y'all, Dr. Brown here with another exciting histology video. This time we're going to be talking about the general histology of bone. That is, how are the cells in the matrix in bone arranged, and what does that have to do with the special characteristics of bone tissue? First, bone comes in two primary arrangements. The first, woven bone, which we see in the transmission EM on the top, and the second, lamellar bone, which we can see down here on the bottom in the GIF image that's switching back and forth between bright field and polarized light microscopy. Woven bone is considered primitive bone. This is kind of early bone that will eventually get remodeled and turned into the more mature lamellar variety. For this reason, woven bone is primarily found in children under the age of 14. After that, most of the bone has now been converted to lamellar bone. However, you can find woven bone in children over 14 and adults, and that's going to be in broken bones. When we heal a fracture, we fill in the space in between the broken bones with woven bone first, and then it gets reinforced with the stronger, more mature lamellar bone. Speaking of lamellar bone, as I just intimated, lamellar bone is mature. This is what woven bone grows up to be. And unlike woven bone, which is kind of a disorganized mess, lamellar bone is well organized. And it's organized into lamellae. It is lamellar, meaning it is layered. You're always going to see a layer of bone cells, or chondrocytes, separated from the next layer of chondrocytes by a band of bone matrix. What we're going to do next is dive a little bit more deeply into compact lamellar bone and the different arrangements of lamellae that can be found in compact bone, and then we're going to finish up the video by looking at the lamellae in trabecular or spongy bone. Compact lamellar bone can have three different arrangements of lamellae. That is, there's three different ways that the lamellae can be packaged together, and we can see all three of them kinda in this picture. The third one we're going to spend a little bit more time on a different picture. The first type or arrangement of lamellae we can find is a circumferential system or circumferential lamellae. Circumferential systems are comprised of lamellae that wrap around, as their name implies, the entire circumference of the bone. So this layer of bone tissue here is going to go all the way around the entire shaft of this long bone. So remember, long bones have a diaphysis or shaft comprised of compact bone, and the circumferential lamellae are going to be on the outer edge near the periosteum and wrapping around the entire bone. The second arrangement of lamellae is the one that you're probably most familiar with, and that is the osteon. The osteon contains a central or haversian canal surrounded by many concentric lamellae of bone tissue. The haversian canal contains the nerve and blood supply for that osteon. Remember, bone is constantly being remodeled. This constant remodeling, breaking down and building back up of bone tissue is going to require an ample blood supply, and the osteon gets most of its blood supply through the haversian canal. There are, however, these transverse perforating or Volkmann's canal running in between adjacent osteons. So although compact bone is very compact, it is riddled with these tiny little passages that allow blood to flow freely through the tissue, ensuring that no osteocyte or osteoblast or osteoclast is too far away from a blood supply. Now, let's look more closely at an individual osteon and the arrangement of its components and talk about how those impart function to the osteon itself and talk about some of the limits of this arrangement of tissues. So first, let's talk about the limits. An osteon is going to have between 4 and 20 lamellae. 20 is usually about the upper limit because as you get further away from the central canal, nutrients and oxygen are going to have to diffuse further and further and further to get to more distant osteocytes. So once you get out to about 20 lamellae or so out, the osteon is simply too big for diffusion from the central canal to the periphery to be efficient. The other interesting thing about the osteon is the arrangement of the type 1 collagen fibers within lamellae. Each lamella has fibers running in an opposite spiral. So you have kind of these spiraling arrangements of type 1 collagen. So it's going to wrap around like so. And then the next lamella out, its collagen fibers would be spiraling in the opposite way. So you have kind of these perpendicular helices. And if you were to look down in this osteon here, the fibers, the type 1 collagen fibers, in adjacent lamellae are running in opposite directions, and these perpendicular overlapping helices are going to impart a great deal of strength to the osteon. This is one of the ways that compact bone gets its high degree of strength, is the arrangement. So it's not just the fact that it's mineralized, but it's the fact that the minerals are laid down on this regular opposing helices pattern within the lamellae. You may remember learning in our unit on connective tissues proper that one of the collagen-related diseases we learned about was osteogenesis imperfecta, or brittle bone disease. In people with osteogenesis imperfecta, their type 1 collagen is incapable of forming these overlapping perpendicular helices, and for that reason, their bones lack that internal structural integrity that healthy bones would have. So we've seen two of the lamellar arrangements in compact bone. We've seen circumferential systems out there near the perichondrium, and we've seen osteons. The third arrangement of lamellae that's kind of visible in this picture are the interstitial systems, or interstitial lamellae. However, I don't like the way it's done in this picture, so I've got another illustration that I'm going to show you that hopefully makes it more apparent how these things come about. Imagine, if you will, we have three osteons. So here you have them right next to each other, and we go into a time where our blood calcium level is getting down to the low end of our normal homeostatic range. Well, we can't have it get below its low end. Blood calcium is one of the most tightly regulated features in the human body. So as soon as calcium starts to get a little bit low, we're going to get an osteoclast develop in the tissue, and it's going to come through the central canal, and it's going to make its way to this osteon. And this osteoclast is going to begin making its way through the osteon, eating the bone tissue per se. What it's really going to be doing is resolubilizing that matrix. So hydroxyapatite is insoluble. The enzymes coming from the osteoclast are going to break hydroxyapatite up into its constituent ions. So you'll get free calcium ions and you'll get phosphate ions. And those ions are soluble, and so they're going to become part of the tissue fluid and eventually make their way into the bloodstream so they can raise the blood calcium level. So as long as this osteoclast is active, and we're going to get rid of the osteoclast and just kind of show you what happens, but as the osteoclast makes its way through the tissue, you can see a hole develops in the bone tissue. That white space is just a gap. We now have a little hole in that bone. Fast forward to a time when now we have a little too much calcium and we need to get rid of it. In comes an osteoblast. And this osteoblast is actually going to be joined by a whole bunch of other osteoblasts, but for the sake of illustration we'll just put one here. But they're going to start laying down new lamellae, forming a new osteon. So now we have a new osteon with its concentric rings, just canonically perfect, but we have these three leftover osteons. We have these three sets of lamellae that aren't perfect concentric rings. They're little pieces of a set of perfect concentric rings. That's an interstitial system. So interstitial systems are essentially what's left over due to this constant remodeling of the bone tissue. So in compact bone, we can have circumferential systems, osteons, and interstitial systems. Trabecular bone, while it doesn't have multiple different systems, is still lamellar bone. If we look closely at this micrograph, which comes from some spongy bone somewhere, I'm not sure exactly where in the human body it came from. In our cartoon here, they're showing you the spongy bone in the epiphysis of the femur. But what you can see is that if we look down here at this bottom portion, the osteocytes are arranged in layers. It is lamellar tissue. So if you were to take this in cross-section, what you would see is still multiple rings. You can see it in the illustration over here. multiple rings. It's almost kind of like an osteon turned sideways. So we still are lamellar. So this is going to be much stronger than it would be if you had the same shape but made out of woven bone. So trabecular or spongy bone, despite its complex arrangement of bone trabeculae or spicules, is still lamellar bone. Okay, so in summary, bone comes in two varieties: woven bone, which is primitive, and lamellar bone, which is mature. Lamellar bone can come in compact bone as an osteon, a circumferential system, or an interstitial system. And then you can also see that in the trabecular bone, we still have lamellae. I will point out here before we close that you don't see blood vessels perforating. Words, Patrick. Sometimes I have a hard time saying my words. I apologize. You don't see blood vessels perforating the trabeculae because these are fairly small, and so there's enough surface area on the trabeculae for nutrients to diffuse in from the endosteum, which is covering the tissue. So that's pretty much it for now. Hope you had fun. Study hard, and I'll see you later.